So the plutonic processes we talked about are all crystallization underground. We had the Mount St. Helens video earlier. Clearly, why are we interested in volcanoes? At least 3 reasons to be interested in volcanoes. The same 3 reasons we're interested in any aspect of geology. What? Okay, so there are hazards. We want to understand the hazards of volcanoes. Not so much of a problem for us around here, but clearly we saw lots of different kinds of hazards from volcanoes, so if we can understand when they're going to erupt, or the likelihood of eruption, or what kind of eruptions we might expect, then we can plan better. Why else?
Shows the history of the area, the geological history.
Okay, so there's some basic geology questions that volcanoes can help us answer. Clearly, volcanic layers are important for absolute dating, as we talked about. It's tough for us to get samples of magma down from underneath the earth, but volcanoes can provide them for us. And as we'll see, there are also some economic resources that can be associated with old volcanoes. So, again, where and how do volcanoes form? We talked about this a little bit before. The problem of getting magma to melt. And so where do we see magma actually being able to be formed? Under what conditions? As we talked about, the lithosphere is one of the most unmelted places because temperatures are hot, but pressures are even higher, and those high pressures, generally speaking, prevent the rocks from melting. So there are 2 conditions where magma can actually get formed. I should do a little pop quiz. What, Brendan?
Flux and decompression.
Flux and decompression. So, in areas where materials are moving up, so you have material that is hot and under high pressures at depth. If that can move up fast enough, the temperature stays high. So down here we've got high temperature and high pressure. And as the materials move up, if we can maintain high temperature but have the pressure go down, then that can allow the rock material to melt. And then that is decompression, melting. And then flux melting is when you introduce water into the system, even though you have the same temperature and pressure as before, the addition of water changes the system in such a way that the melting temperature drops. And so the material that was not hot enough to melt before is now hot enough to melt, even though it hasn't gotten any hotter, because the melting temperature itself has dropped because of the water. So, and these are associated with different kinds of volcanoes. I think we'll come back to that relationship later. So, one of the quiz questions, which of these is true? Okay, is flux melting at locations of mantle plumes true? Grace,
No.
why not?
Because the mantle plume is not where, there's no reason for the melting point to be lower than that.
Right, there's no way to inject water into the system. So flux melting requires water to be injected, so yeah, no, not for that. Alicia, what about B?
No.
No. Why not? What's happening at convergent plate boundaries? Two plates are coming together. One is going down underneath. What's going to happen to the pressure as that plate goes down? Pressure is going to go up. It's not going to go down. So it's not going to be decompression melting at a convergent plate boundary because we don't have the pressures dropping. We've got pressures going up. That's also out. So flux melting at convergent plate boundaries, what's going on there?
Subduction, which means water's going to be produced.
Okay, so you've got the crust that's being subducted. You typically oceanic crust. So it's going to have water in it. And you've got the continental crust. And so down here you've got high temperatures and high pressures. But as this crust gets subducted, water gets baked out of it. Where's the water going to go? It's going to go up. So the water from the oceanic crust gets baked out, gets injected into the continental crust, reducing the melting temperature, and the rocks that couldn't melt before all of a sudden can melt. Okay, so we have mid-ocean ridges. What kind of crust? Is this continental crust or oceanic crust? Oceanic crust. What are the plates doing at the mid-ocean ridge? Spreading apart. So, as those ridges spread apart, material is going to be replaced from where? Yeah, so you're going to get material moving up to fill in the void. So these are spreading apart, so what kind of a plate boundary is that? Divergent. And what kind of magma is going to be produced from melting oceanic crust? Mafic. Okay. So this is the one. So I gave you data from this NOAA site over listing the last 16 years of volcanic eruptions and asked you to just old school list those locations on the map. What? Yeah.
There was 26 years. Started in 1990.
26 years. Okay. 233 observations. So what did you see? Who wants to describe?
There's a lot going on in the Philippines and Indonesia.
Okay, yeah. Actually, this is different data that I'm going to look at than what I asked you to plot. But yeah, there was a lot of the activity was in the Southeast Asia region. What I've got here, I went to the same site and basically they list not individual eruptions, but where are all the known volcanoes. And so this is like 1,500 or more data points, so I really didn't want to have you plot all of those. But I thought it'd be worthwhile taking a look. So we have basically Abu volcano in Japan. It's at 35 degrees north latitude, 131 degrees longitude. It's a shield volcano. So basically I took this data, took it all over into Excel, and so I've got latitude and longitude for 1,500 or so volcanoes. And I started plotting it and I thought, this doesn't look like anything. And I realized I was plotting, by default, given the way the data are listed in the data file, I was plotting longitude on the y-axis. Anyway, they had the data listed as latitude and longitude, so my original plot was, latitude on the x-axis and longitude on the y-axis, which didn't make any sense. So I switched these around, and here basically just did a XY scatter plot, where here is 0 degrees latitude, which is the equator. And here's 0 degrees longitude, which is where? Do people know where 0 degrees longitude is? Prime meridian, which runs through Greenwich, England, because England was the big empire at the time that all this was being determined. Yeah. So, that looks kind of like a Rorschach test. What do you see? It's easier if you put it against the map that I handed out. So what I did was took that map that I gave you, took it into PowerPoint because I don't have Photoshop on my laptop right now. I don't have anything else that can deal with layers. So I put the map onto a slide and then imported that figure. I just did a little screen capture of the graph from Excel, popped it in here, carefully stretched it out to line it up, made it 50% transparent so you can see the outline of the continents behind. And now what do you see? The ring of fire. Okay, so many of you are probably familiar with that terminology. Maybe I should switch over to red here. You've got the ring of fire around the margins of the Pacific Ocean. A lot of volcanoes along the western, along the west coast of South America and North America. What is going on here? Yeah, so we know the Atlantic Ocean is spreading. We know that Africa and Europe is moving away from North and South America. So if the Atlantic is getting wider over time, clearly the Pacific is getting smaller over time. We'll look at plates in more detail later, but we clearly have a Pacific Ocean plate. And here we've got the North American plate and the South American plate. So what kind of plate boundaries are you going to have between in a very simplistic sense, what kind of plate boundaries are you going to have between the North American plate and the Pacific plate? Convergent. And at a convergent plate boundary, unless there are two continental plates, where they're both pushing each other up to form like the Himalaya mountains. If you've got a continental plate and an oceanic plate and they're running into each other, one is going to go under the other, and which is going to go under which? Okay, so basically the North American plate forcing itself over the top of the Pacific plate, pushing it down. Same thing for the South American plate. So that subduction of the oceanic plate is going to take all that watery crustal material and force it underneath the margin of the continental plates here. And so what kind of melting are we going to have going on here? Flux melting. And similar kinds of things are going on over here as well. I mean, basically the Pacific Ocean basin is shrinking because the continental plates are being pushed on top of it. Clearly there's something interesting going on here in the South China Sea and in and around Indonesia and Southeast Asia. We'll have to come back, I think, and talk about that. Seems to be an interesting cluster going on here. Any idea what's going on here?
Well, that's near the Great Divide, isn't it? So that's going to be pushing the edges of the plate into the Indian Ocean, so even more subduction.
No. So, if you look real close here, I should have actually included. Basically, if you happen to travel through Kenya and parts of East Africa, one of the striking features that you see there is the Rift Valley. Basically, that easternmost part of Africa is being pulled away from the rest of Africa, and it's rifting out just like the rifting that took place with Connecticut. So here we have two plates that are pulling apart. What kind of a plate boundary? Divergent. So what kind of melting is going to be leading to the magma that's going on in these areas? Okay, decompression melting. So, if you take all this data, plot it, there's some clear patterns about where we find volcanoes. And actually going back to our history of continental drift and plate tectonics material early in the semester, before there were these ideas about plate tectonics, it was kind of difficult to come up with explanations for why you would be getting volcanoes happening in these areas. And now it's much easier to figure out what's going on. Okay, so this just is reinforcing some of the stuff we've talked about. In the magma chambers, you have different kinds of processes that are going on to alter the composition. We are very interested to know whether the magma that's feeding a particular volcano is felsic or mafic, because that's going to influence the style of eruption on the part of that volcano. And so in this area where we've got divergent plate boundaries, where the mid-oceanic plates are spreading apart, we're going to have mantle material coming up from depth, going to have decompression melting, going to tend to have mafic magma, because this is basaltic oceanic crust essentially that is being pulled up here and melted. Same thing with hot spots over a mantle plume. You've got essentially hot mantle material that's rising quickly enough to stay melted. It's going to be very mafic. And that will influence the kind of volcanoes. In this situation we've talked about a couple of times already now, where we've got oceanic crust subducting underneath adjacent continental crust, and we have this flux melting going on. That melting is going to influence this continental crust, which by itself tends to be more felsic than the oceanic crust. And the felsic material is going to be more prone to melt. And so these situations, we're going to have more felsic kind of magma. So the magma composition is going to influence two properties of the magma. One is the viscosity. The mafic, the felsic magma, because of its higher silica concentration, you have more opportunities for these silica tetrahedra in the minerals that are going to be forming the minerals to interact with each other. That's going to lead to thicker, less fluid, more viscous, less fluid magma that is not going to easily run down and is going to be more likely to lead to explosive eruptions for a couple of reasons. The mafic magma, because it's low silica, is said here, runnier. It's easier for the lava to flow smoothly, less likely for there to be explosive eruptions, more likely to have effusive eruptions, quiet, gentle. This is your nice volcano as opposed to your nasty volcano. The lower viscosity magma makes it easier for gases to escape, and that also ties into how explosive or not the eruptions are. So in general, the more felsic the magma is, the higher the gas concentration. Actually, what this really is the higher the concentration of volatiles. Because at depth, none of the water is not water vapor at depth. The carbon dioxide is not free carbon dioxide gas bubbles at depth. Under pressure, you have no gas bubbles per se, but you've got these volatile compounds, and then when this material comes to the surface, what happens to the pressure? Pressure decreases. So what happens to these volatile materials when the pressure goes down? They expand. They tend to degas from the magma if it's possible. And so it's basically like taking the cork off of a champagne bottle. You release the pressure, all of the bubbles can come out. You get, if you're messy, you get champagne spewing all over the place, and same thing with these felsic magmas. The mafic magmas are going to have lower concentration of volatiles, but also the volatiles have an easier pathway to escape as the material is moving up to the surface, and so the degassing process occurs much more efficiently, and so those gases have escaped by the time the magma is erupting.
So you kind of compare reference size to how you open a bottle of champagne?
What?
You kind of compare the reference size to how you open a bottle?
Yeah, I mean, by the time the mafic magma gets to the surface, it's essentially a flat champagne. You uncork it, nothing's, the maitre d' is going to have to make a little pop sound to make it sound like it's actually good champagne.
It's like running a knife up a semen bottle and blowing it off.
Yeah, that requires you to have a high pressure environment. Okay, so again, this composition that we talked about last time in terms of mafic versus felsic being very important for how, allowing us to identify the different kinds of igneous rocks, also has a really big impact on the type of volcanic eruption that occurs when the magmas of these different types hit the surface. Again, the basaltic or very mafic magma has low silica content. It is much hotter, but because it's less explosive, you get these kind of fairly sedate flows of lava, hot lava down the side of these volcanoes, which is going to influence the type of volcano that is that's formed. And the more mafic or rhyolitic magmas, higher silica concentration, much higher gas, much more likely to be explosive, and will have more opportunities to generate pyroclastic flows, huge ash clouds, some of the issues that we saw with Mount St. Helens. I mean, based on this, what kind of magma would you guess was primarily what we're dealing with Mount St. Helens? Felsic, okay.